C'est bon maintenant. Oui, voilà.
Okay. Belhassen, are you ready?
Yes.
Yes, good. So today we have the pleasure to listen to the talk of Belhassen Dehman from Faculté des Sciences de Tunis. And he will speak about controllability of the wave equation on a rough compact manifold. Well, thank you, Belhassen.
Merci, Sylvain. Thank you, everybody. First of all, I would like to thank very warmly the organizers of this very nice seminar, webinar, I don't know, control in time of crisis. It's a true crisis. Okay, so we will speak about the exact controllability for the wave equation with non-smooth coefficients. Here is the general setting. So I consider this wave system on Riemannian manifold, connected, compact, without boundary, with dimension D, or on a domain of RD with the smoothing of boundary, and in this case you put the homogeneous Dirichlet condition. I consider this system with data in the energy space, H1 times L2, and E of U of at time t is the classical H1 energy of U. In this case, the system is conservative, so the energy is constant. Here is my first figure. It's completely handmade. I like it. It's a bio figure. So here is the domain, and you consider a subdomain, small omega, and the time t. We will choose it suitable to ensure controllability. Also, we will consider a sub-region, subdomain of the boundary, the lateral boundary, the omega, and also a suitable time t. We will call it gamma. We will observe and control from these regions. And the goal of the work is to provide internal or boundary control for waves with non-smooth metric, non-smooth coefficients. By control, exact control, I mean that you want to drive any given initial data to any prescribed final data at the time capital T. By reality, of course, you can drive this data to the rest, state 0, 0, by the action of force, a control vector localized on the domain small omega, if you want to make an internal control, or on the boundary, the subregion of the boundary, capital gamma, if you want to control from the boundary. And we know that by function analysis argument, by Ashrian method, we need for this an observability estimate for the wave equation, for this system, actually. And for observability estimate, of course, there are many types. I can say in this case, you go to the market and you buy what you need if you can pay. For instance, from the boundary, you have this classical estimate. The energy is bounded by some constant times the L2 norm of the normal derivative. Notice in this case that the converse inequality is always true for data in H1 L2. That is called classically as the hidden regularity. Actually, the normal derivative of the solution with homogeneous boundary condition is naturally it lies in L2 of the boundary. And now, for internal observation, we start with the classical one, the strong one. This is that the initial energy is bounded by the L2 norm of dTu on the small omega times 0t. You can replace this quantity by gradient of u, for instance. I call it observability, O. If you cannot achieve it, this estimate, the strong one, you can try to have to prove this one with a relaxing term. Notice that this norm is compact with respect to the H1L2 norm, and to pass from the relaxed observability estimate to the good one, to the strong one, you need, of course, an argument which doesn't depend actually on the properties of propagation or anything, but it only depends on a unique continuation property attached to the small omega subset. And if you cannot prove this estimate, relaxed observability, you can try to prove the observability with loss. So you observe the initial energy by some norm of u on 0t times omega, which is greater than the energy norm. So here you lose some derivatives. We will come back to this estimate later. Last point is to notice that this estimate, the relaxed estimate, can be interpreted, can be seen as propagation of the H1 wavefront of the solution. You can assume, for instance, that the solution is in L2, so this norm is finished, and this estimate tells you that if U is in H1 of the small cylinder, 0t times omega, so it is in H1 of the cylinder, the large cylinder, 0t times capital omega. It's a propagation estimate, really. Other application of observability estimates are, of course, stabilization. Many results of stabilization, like what I mean by stabilization is exponential stabilization of the solution, like this estimate. For instance, you can try to do it for the damped wave equation by this damping term. And also it has many applications in inverse problems like stability results and many other works. Okay, I come to the state of the art, how observability estimates were proved in the literature. In the 18th, they were most of the time obtained by under the global geometric gamma conditions of Lyons. You remember, you take your domain, you take a point outside the domain, you drop the cone, which is a tangent to the cone, and you put your observation region on the side you cannot see from the point. Here you need only metric of class C1, and the proofs were essentially based on multiplier techniques. So it's these proofs are based on, I mean, they were done by hands, pure classical PDEs, integration techniques. In the 19th, we have seen the introduction of a new approach with microlocal tools and microlocal conditions. Here you can see the dates. It can seem a little bit surprising that these techniques go back to the first work by Roche and Taylor in 75, who proved stabilization for the wave equation on a compact manifold without boundary. So they used microlocal techniques, but in this case, of course, there is no boundary. So they obtained estimates that the techniques are the technique we use in the free space. There is no interference with boundary problems. And you can understand it because at this date in 75, we didn't have all the machinery, all the technology of the compressed cotangent bundle of Meroche-Ostrand, which has been done in 92. You can understand in this way that the work by Bardos, Lebeau, and Rauch, the pioneering work by Bardos and Lebeau and Rauch in 92, they can treat the case of domain with boundary, with the same condition, the so-called geometric control condition. It is a microlocal condition stated in the cotangent bundle up to the boundary. Fortunately, these are microlocal and differential techniques. You hold propagation of wavefront sets, support of microlocal defect measures. This condition, geometric control condition, is optimal. It was proved by Burke and Girard in 97. But a priori, it needs smooth metric and smooth boundary. So smooth framework, and a priori, it seems to not work in less regular framework. To our best knowledge, the best result in this way was obtained by Nicolas Burke in 97, who approved observability for the waves for pseudometric, C2 metric, and C3 boundary. It is the less regular statement. In 2040, we find the work, I called it the Oil Theorem of Families Zoisois. OL means observability with loss of Fanelli and Zoisois. They studied the case of the interval 0,1, so one-dimensional case. This wave equation with the density A of x, and they proved that one can have a classical boundary observation, classical one, if A is in the Zygmunt class, and a boundary observation with loss, some number of derivatives, if A is in A of x, is in the log Zygmunt class. And for A of x worse, less smooth than log Zygmunt, there is an infinite loss of derivatives. So they do not obtain observability. In this spirit, we can also see the counterexample by Castro and Zoisois in 2003. The proof of this last result, finally Zoisois result, is based on an exclusively one-dimensional technique, so-called sidewise energy estimates. They interchange the role of time and space and perform hyperbolic energy estimate from the boundary. They solve the wave equation from the boundary. And of course, they use the energy estimates, obtain energy estimates like the one obtained by Colombini, Spagnolo, Lerner, MTV, and finally something as 10 years ago. This is a 1D geometry, and we know in this case all characteristic rays reach the boundary in uniform time. So the question is, what about dimension higher than 1, where the geometry is much more evolved? I come back here with a few words on the geometric control condition. So, a tenor case first, the couple omega t satisfies the geometric control condition if every geodesic of omega is shoot at time t equal to 0 and traveling with speed 1 enters in the set omega, the green one here, before the time t. So this case is good. Of course, here the geodesics are straight lines, and they intersect the boundary following the Snell-Descartes law. And this case is not good, since you have this diameter which never intersects omega. For the boundary, now it's a little bit more delicate. Here, I cannot express the geometric control condition in terms of geodesic. I can do it, I will do it in terms of generalized by characteristics, which are the solution, the integral curves of the Hamiltonian field attached to the wave operator, and on the glancing set, it becomes the gliding vector field. I will explain later. Here you have many kinds, actually 3 types of points of the boundary. Omega is in this side. Here is an hyperbolic point. So you hit transversally the boundary. Here is a point who hits the boundary in tangential way, but if you consider the free by characteristic, it will leave the open set, the domain. So this is a glancing non-diffractive point. Here you have a glancing diffractive, because you hit the boundary and you stay, except this point, you stay in the domain. And here is a glancing point. Here you are solution, not of the curve omega, the characteristic is an integral curve, not of the Hamiltonian field, but of the gliding field. So the first result I will present, is the following. Under geometric control condition, observability or controllability property is stable with respect to small Lipschitz perturbation. More precisely, you take D by D symmetric definite positive matrix. It will play the role of metric. You take also a density kappa of X, real valued function, positive, strictly positive. I will denote a calligraphic A, the pair A kappa, and I constitute in this way the Laplacian, negative Laplacian, and I consider the wave operator PA, dt square minus Laplacian A. For instance, if kappa is exactly determinant of A to the powers minus 1/2, you have exactly the Laplace Beltrami operator attached to the metric A. So the first theorem is, I didn't tell it in the beginning, in the presentation of the talk. All this work comes, of course, from works, joint works with Nicolas Burck from Orsay, Paris Sud, and Jérôme Le Rousseau from Paris 13. I'm not sure about the name, actually. They changed. Okay. So, assume that the pair metric density is smooth, say, of class C infinity or C2 at least, to fit with the work of Nicolas Burke, and that the pair omega t or gamma t for the boundary satisfies GCC for PA. So everything is well defined here. PA is smooth, so you can define the integral curves, the bicharacteristics, and you can talk about geometric control condition. Consider also U epsilon, an epsilon neighborhood of A in the Lipschitz class, and pick some pair B in this neighborhood. So, if epsilon is small enough, the classical observability estimates hold true. Internal observability or boundary observability. They are true for all the solutions of PBU. So the waves that attach to the pair, to the metric B. Of course, under this condition, we get exact probability for PB, the wave operator, with delta B as Laplacian. First remark is that the wave equation is well posed for PB. PB, remember that the coefficients are only Lipschitz. This is well known from the works by Colombini, Spagnolo, and all the team. The second remark is that you have no geometry setting for the metric P. You cannot speak, you cannot talk about by characteristics. There is no geometry. You have only well-posedness. We can take, if you are working on a domain with boundary, you can take a C2 boundary. So this result tells you that under GCC, the observability contability property is stable with respect to small Lipschitz perturbation. But please notice that if you take B, a metric B, in the Lipschitz class, you cannot decide if PB is or is not observable. In particular, if you take B in C1, you cannot say anything. Just a remark before going to some words on the proof. The exact contability itself, this property itself, is stable by perturbation of lower order terms. I mean, the terms are of order 1 or 0 of the Laplacian, of course, but not by perturbation of the geometry or the metric or more generally of the geometry. You can consider the very simple counterexample here. Consider the sphere SD of ID plus 1. If there is a problem, think to R3 and the sphere S2, endowed with its standard metric and with a control domain given by any hemisphere. Here, X1 strictly positive. It's not trivial, it's not very intuitive, but exact probability holds true for this geometry. It was proved by Lebeau in 92. But if you perturb very slightly this domain, you consider this one, omega epsilon, x1 larger than epsilon, it doesn't hold. Even if this control domain is epsilon close to Lebeau's example in the C infinite topology. So, what I want to say here, that if you try to prove this theorem, you can you have to use the fact that it's not the controllability property which is that is stable by Lipschitz perturbation, but the fact that the limit topology, the limit metric satisfies the geometric control condition. I mean, what is stable by perturbation is the proof using GCC, geometric control condition. Our perturbation argument will have to be performed on the proof of the fact that GCC implies exact controllability and not on the final property itself. I mean, not on exact controllability. This is important. 2 words on the proof. I will do it, present it in a simple case. The case of compact manifold without boundary. So you argue by contradiction. I don't want to have problems with the boundary here. It's a very technical and heavy. We have not have enough time. So we argue by contradiction. So you assume that you have a pair, sequence AK of a pair. Remember, AK is the pair metric AK and densities kappa. So AK kappa K, which tends to the limiting pair A kappa in the Lipschitz topology. And for each K, you have a sequence of solutions, so a sequence of initial data, a sequence of solution that of the wave operator attached to a K that violates the probability estimate. So for HP, of course, you have this estimate. If you denote by UK the sequence UKK, UK is of initial energy equal to 1, and the H1 norm of UK, H1 norm on the small cylinder, observation cylinder, goes to 0. This sequence UK is bounded in H1 of the big cylinder. It goes. We will assume this. We will assume that it weakly goes to 0. This is due to the compact term in the relaxed observability estimate. It's a technical details, but we can every time we can assume this. So UK tends to, weakly to 0 in the big cylinder. You can attach to this sequence or make a local defect measure, and the goal is to prove that this measure is equal to 0. And in this case, that means that on H1, in H1 of 0t times omega, the sequence UK strongly converges to 0. And this, of course, contradicts this fact that the initial energy is equal to 1. For this purpose, what we do, we take the limiting operator. P0 is attached to capital A. P0 UK satisfies this equation, difference of the Laplacian. Now you take the differential operator of class 1, classic, and you calculate the bracket P0Q UK in the L2 in L2 of 0t times omega. This bracket is exactly equal to this one plus quantity which goes to 0 with respect to K. And if you calculate this bracket now, roughly speaking, it's a sum of bracket of this type, dg aegk minus aeg0 d di bracket with q UK, it's equal to this quantity. And you have just to analyze this bracket. So the differential operator of order 1 with a function is in the Lipschitz class, which goes to 0 in the Lipschitz class. And here we have the result by Calderon, Kaufmann-Meyer, 85. It's not trivial. It's not trivial. Personally, I try to prove it with paradifferential techniques. I nearly obtained the proof, but at least as long as the one by Kaufmann and Meyer. I'm not sure it's right. Huh? It's safe. So for any function m in the Lipschitz class, the bracket NQ is continuous, a continuous operator from L2 in itself, and the norm of this operator is bounded by the Lipschitz norm of m. That gives you that this operator as operator from L2 to L2 is bounded by this Lipschitz norm, which goes to 0 as k goes to infinity. So this bracket goes to 0, and this exactly means that the transpose of HP0, the Hamiltonian field attached to P0, applied to the measure, micrologarithm measure mu, is equal to 0. And that means that the measure mu is invariant along the Hamiltonian flow of P0. This is exactly the propagation of the measure mu. I mean, when you take some Borelian set, you move it, you transport it with along the flow of P0, of HP0, the measure doesn't change. It's conserved. Okay, 2 words now about the behavior of the HVM control process. I mean, when you change your metric, you can imagine that you are not very safe with the control process. So here is the control problem. You are looking for F, the action you want to make to drive your initial data U01 to rest 00 at time capital T. Assume that omega and T are well done, such that omega T satisfies GCC. By HVM and under GCC, we know that we can choose F as a solution of the transpose equation, the same one actually, in the dual space, with data in the dual space, L2 H-1. So if you want to control this wave equation to find F, you start with U01, and your task is to examine this operator to the state you want to control. You attach the state of the initial data of the control vector. This operator is called the HVM optimal control operator. Optimal because actually the control F we found has the minimal L2 norm. We will denote by FA the HVM control attached to PA, to the metric A, metric and density. We know from now 10 years, more than 10 years, that this operator is very robust. First, it is an isomorphism. between hs plus 1 times hs for initial data to be controlled to the initial data of the controls. So if you improve, if you increase the regularity of the data you want to control, automatically the data of the control vector increase. The control, the HVM optimal control acts almost individually on each frequency block. And if M is a Riemann manifold without boundary, if you drop the boundary, lambda is a pseudo-differential operator, matricial pseudo-differential operator. So it will, for instance, it will gives you precisely the wavefront of the control because it will immediately detect, it will immediately see the wavefront of the data to be controlled. So it appears as a very good operator, but there is a small problem. Look at this. You take a smooth pair, a kappa. We assume that omega t, the control open set and time of control satisfies GCC. And you take any C infinity neighborhood of U of A, as small as you want, you can find a metric A prime in U, as close as you want from A, and an initial data usually 1 with initial energy equal to 1, such that the respective solution, the two solutions, U and V of these two wave equations, look at this. So here it's the wave equation with source, the control attached to A, the good control. Here, the wave equation attached to A prime and the same control attached to A. So here, if you consider this equation with this data, at time capital T, U will be 0. But here, it's not the same. So, I mean, if someone makes a mistake, he uses the wrong control. What you can see at the final time, capital T, you see that the energy of the difference of the two solutions, which is equal to the energy of V, because U is equal to 0 at capital T, is greater than, I say 1/2, but you can put any strictly positive constant. And the L2 norm of the difference of the two control vectors is bounded by below by some positive constants, depending only, I think, of course, it depends on the time, capital T, and it depends on the coefficient of the Lipschitz norms or something like this. We would say coefficients which are completely geometric. So that tells you that for fixed initial data, the map that attached to every pair A kappa control vector is not continuous. Notice here just that since A prime is very close to A, GCC is the geometric control condition is also satisfied by omega t for the metric A prime. So F A prime is the control F A prime is well defined by HVM method, of course. If you look at the proof, you will see very quickly that this result doesn't work. It's not valid for control of smooth data because actually it uses really the behavior of high frequencies of the solutions. The proof consists just in choosing A prime equal to 1 plus epsilon A, very small perturbation of A. But this gives you that the characteristic sets of the two wave operators intersect only on 0. And you can do the job with this. I have no time to detail the proof. Okay, so here, 15 minutes yet. Okay. I remind the goal, prove observability estimate for the waves with the matrix. I remind also the strategy, we will prove relaxed estimate, and we drop this term by unique continuation argument, and we will work by contradiction. And essentially, we will use propagation or make local defect measures. So to be achieved prove propagation result for mu in a low regularity setting. Here is the problem. This is the gap. Very easy point. We start with the ordinary differential equations with the continuous coefficients. For instance, study the propagation properties of a non-negative random measure on RD subject to transpose X mu equal to 0 in, of course, in a distribution sense. I mean, mu applied to X key equal to 0 for every key in C01. X is a vector field with continuous coefficients. The simple case is the case of X with smooth coefficients, for instance, C1 or Lipschitz. Naturally, it admits a flow, phi s of X, X1, X2, Xd of S, satisfying this equation, Hamiltonian equation, starting from the point X. You take key, function test key in this space, and you say that this quantity is equal to 0. Okay, it's equal to 0, but it's also equal to this bracket, this one by definition of the flow, and of course you can the S derivative can leave the bracket since mu is linear and continuous and so on. So this is equal to 0. So this quantity is equal to 0. That means that mu applied to key phi of S is equal to mu key phi of 0, that is key. And they say to you that there is propagation for the measure mu. You can key, imagine, for instance, that key is the indicatrice of some Borel subset. So the transporter of the set and the set itself have the same mu measure. So mu is invariant along the flow of the vector field X. Here is our theorem concerning the propagation. This is a theorem that was proved in 2013 by Ambrosio and Kripa, and in 2019 by myself, Burke, and Jérôme Rousseau. If you consider vector X with vector field X with continuous coefficients, non-negative random measure, solution to Tx mu equal to 0, then the support of mu, please, it's written in red, the support of mu is a union of maximally extended integral curves of X. I mean, here we lose something very important. Mu is not invariant by the flow of X. We have just an information about the support. In other words, if x0, the point x0 is in support of mu, then there exists a neighborhood of x0 and an integral curve gamma of x such that x0 is in gamma, and locally this gamma passes through the point x. Locally, this integral curve gamma is contained, completely contained in the support of mu. I have, voilà, beau dessin. This figure, look at this, you have the point x0. Notice that in this case, since x has continuous, only continuous coefficients, you have no uniqueness of the integral curves. You lose the uniqueness. You can construct, you can obtain integral curves by the Peano theorem, but you have no uniqueness. So through this point x0, you can have here, I draw the 4 integral curves, no problem. But what this theorem tells you is that one of them, at least one of them, is locally contained in the support of mu. For me, it's the green one. In particular, of course, if the trajectory is unique, there are many examples, many cases where the trajectories are unique, even if the coefficients are continuous, then all the integral curve gamma lies in the support of mu. So actually, this result expresses a propagation of the support of the measure. I notice here that the result by Ambrosio and Kripa is only valid in the free space, away from the boundary. While this proof, the proof we produce, will also, and this is the heart of the problem, our proof will also work on the boundary, up to the boundary. The positivity of the measure is crucial, important. The proof relies on simple argument, Ascoli theorem, less simple argument, technique of positive commutators, which was developed for the first time, if I remember well, for the first time it was developed by Melrose and Chostrand in their paper for propagation of singularities up to the boundary in the beginning of the 18th. And the main result is the following. Assume that the pair metric density is of class C1. Class C1, that means that the Hamiltonian field attached to the wave operator is continuous, only continuous. And assume that omega, the domain omega, is of class C2. The boundary is of class C2. You know that if your metric is Ck, the boundary has to be at class of class at least Ck plus 1, since every change of variable make you lose one derivative. So assume also that omega t and gamma t satisfies the generalized geometric control condition. If you try to write this condition, you will rewrite exactly the same condition. Here, it's exactly the same statement, but you have to understand that there is no uniqueness of the integral curves. There is no uniqueness of bicharacteristics. Through any point, you can have many integral curves of the Hamiltonian field or the gliding field. So under this condition, you have the classical observability estimates for this operator. And of course, as a corollary, you have a controllability. unfortunately, in this case, I have some words to our friends who are not used to this thematic. If someone tells you, I will use my colloquial defect measures to prove this result or this other result, please ask him what my colloquial defect measures you use. They don't say it. Generally, because it's clear in the mind, but it's not believe me, it's not clear at all. Here, if you try to prove this problem with this estimate, like I did it in the case of a compact manifold without boundary, if you try to do it with my colloquial defect measures, which live on the co-sphere bundle, which you handle with classical differential operators, it doesn't work. It's not possible to prove it with my colloquial defect measures. So we have to switch and to use semi-classical measures. For this, of course, the set of test functions, of test pseudo-differential operators, is not the classical ones, but the semi-classical pseudo-differential operators. So I start with semi-classical setting. Here I present the Ashton differential calculus. You define this symbol. I have not much time. You can consider this symbol, which are in lock with some condition. Most of the time, we use A of X and Xi in the Schwarz space. So it's not very complicated. You quantize, I think we say like this. These symbols, you make a differential operator in this way. Here you see you have the small parameter H. Afterward, we'll call it a scale. They are continuous on L2. We can bound the norm very easily. You can also consider the bracket with continuous function. It's really wonderful. If your function is better than continuous, if it is in the Lipschitz class, you can bound the bracket more precisely. The tools are very simple, Schur, Lemma, and you can define the semi-classical measures by using, as I said, as test functions, these pseudo-differential, semi-classical pseudo-differential operators. They enjoy the same properties, nearly as the classical colloquial defect measures, support localization, propagation up to the boundary. You can, with smooth metric, in the smooth framework, this work was done, of course, by Nicolas Burck and Patrick Girard in 2 different papers, and Gerard Lechtam also. And we obtained for this what I called propagation equation. It seems very mysterious. Here, it's an identity between in the space of distribution, of course. Transpose of the Hamiltonian field applied to mu is equal to some integral of a measure. Remember, please, that when your sequence UK of solution is bounded L2, in H1, excuse me, this is wrong, in H1, the sequence of normal derivatives on the boundary is bounded in L2 of the boundary. Okay, so we can attach to it also some measure mu. These are 2 semi-classical measures, and they satisfy in the sense of distribution this equation. Here we integrate over the hyperbolic set and the cleansing set. This identity takes place in the distribution of the cotangent bundle on the boundary. Technically, it is the most delicate point to prove. It's classical, but with non-smooth coefficients, it's a little bit more delicate. But okay, that was good. We had to prove completely Bell-Roche-Ostrand setting for continuous Hamiltonian field HPA. I have 1 minute. I will just show you. I will prove this propagation result, this one, away from the boundary. We have no time, just with some figures. The idea is to start from a point X in the support of the measure mu. The vector field X is here. You take the value X of X. You assume, of course, that X of X is not equal to 0. You drop X, you draw X of X, and we can prove that if you take for every epsilon, for delta enough small, the ball, if X is in the support of the measure mu, the ball X of center with center X delta plus delta X of X and of radius delta epsilon intersects the support of mu. I mean, you drop this, you move your X, you consider this ball with center X plus delta n X of X and with radius delta n by n. We prove that this ball intersects the support. So there is another point. You do again, apply again this process, and another time, and another time. And the idea is this line is a continuous curve, which is, these are segments. I mean, these are straight lines. Each one of these points is in the support of the measure. The idea is to prove, ça marche pas. That the limiting curve, so you consider a curve. The idea is to prove that the limiting curve is solution of this equation. This is possible by extraction, applying the Ascoliar-Zella theorem. And this curve is, of course, an integral curve of X and is completely contained in the support of mu, since it is close. I will stop here. Thank you.
Well, thank you, Belhassen. Oh, I'm the only one to applaud. That's okay, but I'm sure that everyone is very happy with your talk. So maybe I think we have time for questions. So if there are some questions, please feel free to open your microphone and to ask. Well, okay. Or you can also ask it in the chat, and I can tell them if you do not have a microphone. Okay, so let me start then. I have one question for you, Belhassen. So
Yes.
here the proof you are given for the observability of the waves are all based on some kind of contradiction argument.
Yes.
So at the end, the constants you have are not explicit at all. Is there any way to get some more precise bounds? Something which is, say, a constructive proof or something like that?
Good question. You can obtain it in some sense an estimate of the constants if you, for instance, use Kalman estimates. It is possible in some cases.
But can you do Kalman estimates under the geometric control condition?
No.
Yeah.
No, not because this condition is optimal.
Yeah.
I agree. You gain optimality, but you lose the constants. Sure. But almost all these estimates don't give you information on the stability constants, of course.
Mm. And so maybe also in similar spirit, so can you, so I remember in your work with Lebeau, you expressed the principal symbol of the Hume operator. Here you are in a setting in which you have observability, so you have a Hume operator which is well defined and is invertible. Is there anything similar, say, to a symbol for those class of operators?
What we proved that your gramming, your HUM operator is elliptic, and we know we express the principal symbol.
Mm-hmm.
Now, you have just I mean a very you have an estimate of this constant as the continuity modulus of some elliptic operator.
Okay.
For which you only know the principal symbol. You see.
But here, in the case of a C1 velocity, the Hume operator has no. What is that? Is that a pseudo-differential operator? Certainly not, right? So what is the meaning of
I
a
can
principal
answer
symbol?
for velocities which are better than C2.
Okay.
Look, the work with Lebeau concerned smooth metrics of class C infinity. So nothing is done this way for less regular metrics. But for metrics better than C2, it's a progressing work in progress. The HUM control operator is almost sure is a paradifferential operator, elliptic operator. Okay. And the expression of the principal symbol is the same, but it is in a paradifferential field. It is a paradifferential operator of order 0 elliptic also. It works well. This result is only true, of course, on compact manifolds without boundary. For the moment, it works in this way.
Okay. Thank you very much, Belhassen. Is there any other question?
Okay, I have a question, but I don't know if it is the appropriate, but is there any connection to some kind of nonlinear waves in terms of perturbations that can be used to deduce something for a nonlinear equation?
Good question, Enrique. Good question. Of
We are
course.
the organizers.
Oui, sure. Sure. Because if the coefficient will depend on the solution, of course you will be in this framework, in this situation. It needs work. But what this result says that we can deal with a C1 metric. It's possible. But as you can see, you will not be able to find, to prove that this condition, what I call GGCC, generalized geometric control condition, you will not be able to prove it is necessary. Because you have no uniqueness of the integral curves of the material field. So it is difficult, really. I lived some bad experiences with this, but for the moment we have no good answer. But you can allow C1 coefficients, that's sure.
Okay, so I think, well, thank you. I think there's a question by Jean-Pierre Puel.
Oui.
Jean-Pierre?
Yes. So this condition GGCC cannot be, as it is explained, you explained, it cannot be necessary.
Yes, you're right. We are not able to prove its necessity in general.
But my question is, well, do you conjecture that among all candidates for trajectories for the flow, you have no uniqueness in general?
Mm-hmm.
There should be a selection.
Champion.
By some criterion, I don't know, the least something, least path, or the least.
For a long time we have think to this issue, and there is no, let me say, an objective criteria of selection of. Look, Jean-Pierre, if you, for instance, you try to, by convolution, you can smooth the coefficients of the metric, and you will obtain a family of flows.
Yeah.
You are not able to select which flow will carry the support of the measure or something like this. You are not able to do it. We cannot select already.
No, in general.
In general, yes. That what you can do is that was the proof followed by Kripa and Ambrosio, exactly. Okay. They prove there is one, comment dire,
there is a selection.
Integral curve, exactly, integral curve that is completely, that lies completely in the support of mu. But unfortunately, there is no way to make this.
They can select among the
No.
non-uniqueness, they can select one integral curl.
Yes, but in the free space.
Yes, okay.
On the boundary, it doesn't work.
And you know which criterion they have? Least length of I don't know, something like that.
This is done by tout simplement by they know there is a convergence for some subsequence. C'est as connu.
But if I may, so in the case of geometric optics, when I was a student, I remember this Fermat principle saying that the light will go the fastest possible, I believe, or something like that. So maybe there's a way, because it comes from a wave problem, a wave propagation problem, maybe there is some kind of selection in there, right?
You are right, because Sylvain, you see, the propagation result we proved here. Forget about the boundary. That doesn't know that X is the Hamiltonian field of wave operator. It's general. You're right. Probably you're right. We don't use nowhere that we have a wave equation.
Yeah.
Sure. Of course, the wave equation will come here. This is crucial, that you have the dimension.
Yes.
These are the Dirac distribution in Xi plus, Xi minus, hyperbolic. Two hyperbolic fibers issued from Rho.
Okay. Is there any other question?
But if you read, I didn't do it. If you read carefully the paper by Meroche-Ostrand, you will see that nowhere they use uniqueness of integral curves. There is no uniqueness. They
Thank you very
don't.
much.
Oui.
Sorry, I have a question.
Yes.
I go back to the time of controllability.
Yes.
Is because for the wave equation, we have to sometimes an abstraction of the time of controllability. The capital T.
Yes.
Is here. There is no abstraction for the time of controllability.
Yes, but you assume that you have a geometric control condition. It's large enough.
This abstraction is replaced by the geometric
control condition. Yes, the condition actually reads on the pair omega and the capital T. For instance, if small omega is equal to the whole domain, the whole manifold, you can take T as small as you want. There is no problem. If you control everywhere, you can take T as small as you want. The condition reads on the pair actually.
Okay. D'accord. D'accord. Merci, Belhassen.
Merci beaucoup.
Ok. Sylvain, tu as désactivé le microphone. Les micros.
Moi, j'ai pas de...
Oh, okay. Is there any other question?
Yes.
It seems that there are another question, Omar.
Yes. Okay. Thank you very much for your interesting presentation. I have a question about the observability inequality to get the controllability. Normally, in the right-hand side, we have to prove. I don't know if we have to prove the observability inequality with the state in the right-hand side or with the time derivative.
So here, let me this one. Here, you are talking about this?
Yeah.
Okay, but
Yeah.
here I consider observability estimate in H1. The energy is the H1L2 energy. So here you have the normally you have the H1 norm on the small on the observability observation region. You can replace if you want. It's locally. It's surely right. You can replace this time derivative by gradient, for instance. This is possible. But now, if you try to get observability estimate in L2 H-1, of course, here you will have L2 H-1 norm, and here you only the wave, of course. And here you will get, for instance, H-1, H-2. You can get
Yes.
one level, one step down, of course.
Okay, is there any more question? Well, if not, sorry.
Another question, please. Is there some relationship between internal controllability and boundary controllability? I don't know if we can deduce, for example, the boundary controllability
from internal controllability
by extending the region.
Internal from boundary, yes, of course, yes. It's well written.
Okay.
If you look for something very simple, it's very well presented in the book by Lyons. It's well described. You can get a neighborhood of, you take a region of the boundary that controls the domain, and you take a neighborhood in omega of this region, and it will work. It will control.
Thank you very much. Thank you.
Voilà, internally. Voilà.
Thank you. So, is there any other questions?
Normalement, on passe à la salle de café maintenant, mais malheureusement.
Voilà. So, if not, let's thank again Belhassen. So, the only ones you can hear probably, but I'm sure that everyone has been very pleased by your talk. And so next time we have a junior session with Kevin Lebalch and Jean-Nazier Barsena-Patisco. Okay, well, so thank you to all of